if we look at all the linear maps from a vector space back to itself, it actually forms what is called an algebra. So this is a term, it might be unnecessary jargon, but the book sort of dances around it. I thought I'd just come out and actually use it. It goes like this. Suppose A is a vector space. Vector space over F. Now, if A is equipped with a bilinear product there we go. Equipped with a bilinear product, then A is called an algebra over F. Okay, and so here's this crazy blue phrase, equipped with a bilinear product. What does that mean? It means we defined a product. We defined a way to multiply. So if you've got a vector space and there's a way to multiply vectors together, then you have an algebra. Okay, and so just to be specific, this means we've defined a way to multiply vectors. So this is going to be a map. I'll denote it with a dot, and it sends a pair of things from our vector space and spits out a new thing from our vector space. Okay, so it's a binary operation. It's an operation that takes two arguments, and it spits out a single thing. And it has to do it in a way that satisfies the distribution. So x plus y, if you multiply that on the right by z, that you should get x times z plus y times z. And if you multiply on the left, it should distribute, which looks obvious, but actually doesn't follow as an axiom, so you have to have it as part of the definition. And it needs to behave nicely with respect to scalar multiples. So if I have a vector x, and we take a scalar a from f and multiply it like that, and I have a vector y, and it's been scalar multiplied by some b from f, then the product of these two things, however the product is defined, it needs to make sense that this satisfies, well, first you multiply together the two scalars, and you use that as the scalar to scalar multiply x times y. Yep. Okay, and so that's what it means to be a bilinear product. This is the bilinear part. And if you check the multiplication that we defined in the last clip by composition, it satisfies all of these. And this is basically the justification for why we call composition a multiplication, because it distributes over addition and it treats scalars properly. And so it's a theorem that if we equip LVV with the product defined by composition, then LVV becomes an algebra. So the proof of that theorem is just verifying the properties that I wrote in blue just above. And in fact, it turns out to be a special algebra. It's an associative algebra. So not everything fitting the definition of algebra has to satisfy this, but composition does. You can move the parentheses around in a product. That's the associative property. And it's also an algebra with identity, because the identity map, so the linear map that sends V to V by keeping everything exactly where it is also an identity in another sense, namely it's the multiplicative identity of this algebra. That was, well, okay, that's sort of an ick, whatever. Multiplicative identity. For LVV. And so you notice here that I'm not talking about LVW, and that is because of the thing I mentioned in the last clip, which is that the codomain of one map has to match with the domain of the other map, or the product might not be defined. So to ensure that it's always defined, I'm using V for both domain and codomain. And so once upon a time, I talked about a bunch of other words that we're not going to use again for the rest of the course. I talked about groups and rings and fields. And I said that fields are a subclass of rings. Namely, there are ones where you have, there are rings where you have multiplicative inverses. And then groups are a simpler object altogether, where you don't even have the multiplication. And then, so over here we have something sort of similar going on, where in the most general case we have these things called modules that you don't ever talk about outside of a grad class typically. And then we have vector spaces, which is the special case of a module where the scalars come from a field. And then you have algebras, which are a special type of vector space where you can actually multiply together vectors. There we go.